Every year, over 2 billion tons of trash are generated worldwide. It's as if every inhabitant of the planet threw away 5 kilograms of waste every day. But did you know that this trash is now not just a problem, but a goldmine for a new industry? In workshops where just yesterday, dirt and danger reigned, today high-tech hunters are at work. Robots that see more than the human eye and can sort in seconds what humans struggled with for years. And this is just the beginning. If you watch until the end, you'll find out how one teenager's idea changed the fate of the entire ocean. The waste management sector is undergoing a technological revolution thanks to the implementation of artificial intelligence and robotics. At modern recycling plants, robotic manipulators, controlled by complex algorithms, sort waste with incredible speed and accuracy. Computer vision systems identify different types of materials, such as plastic, glass, paper, and metals, which significantly increases the recycling rate and reduces the amount of trash that ends up in landfills. On a wide conveyor belt, a continuous, chaotic stream of what we've thrown away. Plastic bottles, crumpled cardboard boxes, aluminum cans, milk cartons, glass bottles. To the human eye, it's just trash, almost impossible to sort through. And for a human worker, it's hard, dirty, and dangerous work. And so, above this stream, like a relentless hunter, it hovers, the sorting robot. This isn't a humanoid android from science fiction movies, but rather a high-tech industrial manipulator, similar to a giant steel arm mounted above the conveyor. But all its magic is inside. Its eyes are not just cameras. They are complex multispectral sensors that see the world differently than we do. They can distinguish materials by how they reflect light, analyze their chemical structure, and shape in a fraction of a second. The heart and brain of the system is artificial intelligence. Before getting on the job, this AI underwent intensive training. It was shown millions of images of different types of waste, just like you would show a child a million photos of apples until they learned to recognize them flawlessly. In the same way, the robot learned to identify PET plastic, used for beverage bottles, HDPE, a denser plastic for canisters and bottles, paper, cardboard, various types of metals, and glass. And so the action begins. The conveyor is moving. The camera continuously scans the stream. The AI analyzes the images in real time. Target identified. Aluminum can. It sends a signal, and the steel manipulator makes a lightning-fast, almost imperceptible to the eye, move. A pneumatic suction cup, or a mechanical gripper, gently but firmly grabs the can, lifts it above the stream, and with a precise movement, drops it into the corresponding container on the side. Before the can has even landed, the robot's eye has already spotted a water bottle, and the arm flies to a new target. Speed? A human can't compare. Some models can perform 100 manipulations per minute. That's more than 1 grab per second. Accuracy. The robot doesn't get tired, doesn't get distracted, and doesn't make mistakes due to inattention. Its sorting efficiency reaches over 95%, which significantly improves the quality of secondary raw materials. It can work around the clock, stopping only for maintenance. This isn't just a replacement for manual labor. It's a quantum leap that makes recycling much more efficient and economically viable, turning the problem of trash into a real resource for a new industry. The sorted materials, piles of hard plastic, bulky metal structures, wooden pallets, lie in separate mountains. They have been sorted, but are still too large, too awkward to be given a new life. This is where the true heavyweight of the recycling industry comes onto the scene, a machine whose job is controlled, brutal force. This is a rotary shredder. Externally, it looks like a huge steel box, but its heart is a massive heavy rotor, studded with rows of extremely strong, hardened steel teeth or hammers. This is not just a machine. It's an insatiable beast, powered by a powerful motor that provides colossal torque. Its task is simple, but critically important: to shred. When material is fed into its huge maw by a conveyor or a manipulator, be it an old car bumper or a whole pile of plastic barrels, a spectacle of unstoppable power begins. As it rotates, the rotor's teeth grab the objects, pull them inside, and with a deafening roar and grinding, tear them into pieces. There's no room for delicacy here. Hard plastic cracks, metal bends and tears, wood turns into splinters. This process is a demonstration of pure physical force, aimed at one goal: size reduction. But why this destruction? It's not senseless annihilation, but a key preparatory stage. First, the shredded materials become uniform in size, making them much more convenient for transportation and further processing. Second, it's a process of liberation. The shredder breaks down complex objects into simpler components, making it easier to separate different materials from each other in subsequent stages. And most importantly, it creates the ideal raw material for further recycling. A pile of small plastic pieces is much easier to melt in a granulator than whole bumpers. Huge accumulations of plastic in the world's oceans, such as the Great Pacific Garbage Patch, are one of the most acute environmental problems of our time. By the way, do you believe that this patch doesn't exist? However, thanks to bold engineering solutions, there is hope for cleaning up the marine spaces. The problem is so gigantic that it seems unsolvable. How can you clean up something the size of several countries? Most people just threw up their hands, but not Dutch teenager Boyan Slat. In his mind, a bold yet brilliantly simple idea was born, which grew into one of the most ambitious environmental projects of our time: the ocean cleanup. The principle of the project is not to chase plastic all over the ocean, but to make the ocean itself deliver the garbage to a trap. For this, giant U-shaped barriers were created. This is not just a net, but a complex engineering structure consisting of a long, floating boom on the surface that prevents plastic from floating over it, and a deep mesh skirt underwater that traps the garbage, but allows marine life to swim freely underneath. The most interesting thing is how this system moves. It has no engines. It passively drifts, carried by the same forces that move the plastic: wind, waves, and ocean currents. But thanks to its design and a large sail above the water, the system moves slightly faster than the plastic passively drifting in the water. This creates a small but constant difference in speed. The barrier, like a giant shepherd, slowly but relentlessly gathers its plastic flock inside its U-shaped arch. The path to success was not easy. The first prototypes broke under the pressure of ocean storms, and unforeseen engineering problems arose. But after a series of trials, errors, and significant improvements, the system began to work effectively. Now, from time to time, special support vessels approach the filled barrier and, like giant garbage trucks, unload the collected tons of plastic. This plastic, from old fishing nets to tiny fragments, is brought to shore, where it is sorted and sent for recycling, closing the loop. Thus, an idea born in the mind of a young dreamer has turned into a real, working technology that offers hope for cleaning our oceans. Realizing that cleaning up the ocean without stopping the flow of trash entering it is like bailing water out of a leaking boat, the ocean cleanup team asked themselves a logical question: couldn't we just plug this leak? After all, research shows that the vast majority of plastic enters the world's oceans through just a small number of the most polluted rivers in the world. Thus, the Interceptor was born, a technology aimed at tackling the problem at its source. It looks like an elegant, futuristic catamaran, anchored in the middle of a river. It is completely autonomous and runs on 100% solar power, thanks to the panels covering its upper part. Its design is thought out to the smallest detail to be as effective as possible and not to interfere with navigation. Every minute in the United States, over 1,000 feet of copper pipe is manufactured. But behind this seemingly simple component lies large-scale production, explosive temperatures reaching 2,000 degrees Fahrenheit, and even espionage investigations. From molten lava in furnaces to laser marking under ultraviolet light, each pipe follows a journey straight out of a movie about industrial superheroes. And did you know that some people are audacious enough to counterfeit copper just by painting its surface? This story is about how real pipes are made and how to distinguish the genuine article from a dangerous fake. Let's dive into a world where every second equals a ton of metal. It all begins underground, in the copper mines of Arizona or Montana, where hundreds of thousands of tons of copper ore are extracted each year. It's crushed, washed, purified, and the output is shiny granules of pure copper. These granules go into smelting furnaces, where temperatures exceed 2,000 degrees Fahrenheit. Here, the copper transforms into molten lava. The molten copper is poured into long molds, so-called slabs, or ingots. They resemble thick orange beams, glowing white hot. These ingots are destined to become pipes, but there's still a long way to go. Pure copper in the form of ingots or cathode plates is loaded onto railroad flat cars, trailers, or even ships, and transported to rolling mills or pipe manufacturing plants. Cathode plates are thick metal sheets, approximately 3.3 inches by 3.3 inches, weighing up to several hundred pounds each. At the plant, the ingots or cathodes might first undergo additional remelting to achieve the required purity or desired shape, for instance, round billets for pipes. Then, they are heated and sent to the rolling mills. Rolling lines operate with machines boasting over 10,000 horsepower. The ingots are sent to rolling stands, machines weighing tens of tons. Giant rollers crush the hot metal, transforming it into long strips. The sight is incredible. The red-hot copper stretches out, sparks fly everywhere, and nearby, streams of water cool the metal, turning it into a shiny, almost mirror-like sheet. In modern workshops, all of this is controlled by computers. An operator sits in a glass cabin, similar to an airplane cockpit, monitoring dozens of screens. Here, every temperature, pressure, even the sheet thickness is under control. If anything goes wrong, the automation instantly stops the line. Now for the most interesting part. The copper sheets are cut into blanks. In plants where the copper sheets are still hot after rolling, powerful hydraulic or mechanical shears are used for cutting. They look like giant guillotines with massive steel blades. The sheet moves along a conveyor. An automatic sensor determines the exact cutting spot. The blades descend with immense force and slice off pieces of the required length and width. What do I mean when I say, with immense force? Sometimes it's tens of tons of pressure. All this happens in seconds, often while the sheet is still moving. That is, the line doesn't stop, and the guillotine cuts on the fly. For certain formats or thinner sheets, rotary knives are used. These are rotating steel discs that cut the copper as the sheet moves. It looks a bit like cutting pizza, only on an industrial scale. This method is suitable for narrow strips, or when the sheet needs to be cut, not only crosswise but also lengthwise. In modern factories, laser or plasma cutters are used for complex shapes or high precision. A laser beam or plasma arc heats and vaporizes the copper at the point of contact. This results in a perfectly smooth cut, almost free of burrs. Lasers are used for non-standard parts or when special geometry is required. After the main cutting, the blanks may pass through special edge trimming machines that remove irregularities, sharp edges, or excess material. The cut blanks are fed into drawing machines. This is a huge press that draws the copper through a steel die. The output is a perfectly round, smooth pipe. All this happens in mere seconds. The machinery operates at incredible speed. At large plants, like Mueller Industries, they can produce over 1.5 million feet of pipe in a single shift. That's, no lie, like the distance from Chicago to Detroit. Each pipe undergoes automatic inspection. Laser scanners search for microcracks and defects, and special robots select samples for additional testing. After being drawn from the red-hot die, the copper pipe is still hot, flexible, and prone to deformation. To quickly give it stability, the pipes are automatically directed onto a conveyor, leading to special cooling pools. Inside is cold water, which creates clouds of steam upon contact with the incandescent metal. This sharp temperature drop locks the pipe's shape, preventing it from bending or losing its geometry. Cooling takes only a few tens of seconds, but is crucial for quality. Next, the pipes arrive at the precision cutting table. Here, They are met by automated robots equipped with cutting discs or hydraulic knives. They measure the length with laser sensors and quickly cut the pipe according to the standard. For example, 10, 20, or 40 feet, depending on the order. Cutting accuracy reaches tenths of a millimeter, and the speed is up to several hundred pipes per hour. After this, the pipes undergo quality control. Laser scanners check the external appearance, looking for cracks, burrs, or other defects. Rejected pieces are automatically sent back for remelting. Those that pass inspection continue along the conveyor to the marking machines. Here, a laser mark is applied to each pipe. It encodes the production date, batch number, sometimes even a QR code for tracking. This allows for precise identification of each pipe in case of claims or the need for quality analysis. After marking, the pipes might still be slightly damp from the cooling water. To prevent corrosion and ensure a perfect appearance, they are moved into drying chambers. These are tunnels with powerful fans and heating elements. In just a few minutes, the moisture completely evaporates and the pipes acquire their characteristic copper sheen. Next comes the packaging stage. Here, robotic manipulators come into play. They pick up the pipes using suction cups or grippers, very carefully stacking them into bundles of 10, 50, or 100 pieces, depending on the diameter and length. The robots work with surgical precision to avoid damaging the pipe surface and prevent deformation. After forming, the bundle is secured with metal or plastic straps for reliable fixation. Some plants add protective film or cardboard inserts to prevent scratches during transport. The finished bundles are automatically moved to warehouse platforms. There, each batch receives a logistics label with all the data about the manufacturer, dimensions, production date, and final recipient. Then, loading onto trucks or railroad flat cars. Everything happens as quickly as possible. A modern plant can prepare thousands of tons of pipe for shipment in a single day. Thanks to automation, this stage minimizes human involvement, ensures safety and accuracy, and guarantees that the pipes will arrive at the customer in impeccable condition. Oh right, I promised to tell you about the spy games. This is a real detective approach in manufacturing. Due to the high price and constant demand for copper, temptation arose for unscrupulous manufacturers or intermediaries. They started counterfeiting markings and passing off cheaper alloys or even other metals as pure copper. Fraudsters became so brazen that they began forging documents and selling bootleg goods under the guise of reputable brands. Counterfeits can be dangerous. They often fail under pressure or corrode faster. A rupture in such a pipe can cause accidents, flooding, or fires. Counterfeiting scandals have occurred in many countries when it was discovered that a copper pipe actually contained only a thin layer of copper, with cheap metal inside. Manufacturers spent years building their reputations, and counterfeits under their name could lead to mass recalls and lawsuits. Therefore, pipes are now marked with invisible inks visible only under ultraviolet light. This helps combat counterfeiting. Every year, the world produces over 200 million kilometers of cable, enough to wrap around the Earth 5,000 times. But few people know that the heart of every electric car is not just the battery, but also a cable that can withstand voltage, temperature, pressure, bends, and vibration. How are these high-tech wires created, capable of working in conditions where even metal seems alive? How do scrap, dust, and molten aluminum turn into the arteries of Tesla, Rivian, and Lucid? In this video, the whole truth about the most engineered wire of the 21st century. Every cable for an electric car is a strategic choice. It must be flexible but not brittle, conductive but not vulnerable, lightweight but capable of withstanding hundreds of amps and thousands of hours of voltage. And when engineers sit down at the drawing board, they are like alchemists of the future, mixing formulas of elements in their heads, searching for the perfect balance. Copper is the good old classic. It conducts electricity better than anything else, and it's its heart that beats in most cables. But the weight, oh, that weight! An electric car needs to be as light as a cat, so aluminum often steps in as a substitute. It's cheaper and lighter, though not as conductive. But in the right alloy, it's already a weapon of the electric age. And around it, insulation. These are highly engineered polymers that can withstand heat, cold, chemicals, vibration, dust, and even a small lightning strike under the hood. They lack the shine or weight of metals, but without them, everything would turn into a sparkling inferno. Some cables have shielding, a thin armor of copper braiding or aluminum foil. It protects signals from interference, because in an electric car, not only kilowatts are important, but every millivolt of data too. Aluminum isn't born shiny. First, it's rough ingots, each weighing over 1,000 pounds. They arrive at the factory like aliens from their ore world, extracted from bauxite, purified, remelted, and finally formed into rectangular blocks resembling metal sarcophagi. These ingots arrive in large trailers, carrying tens of thousands of pounds of the future. By appearance, they are just shiny silver blocks, neatly stacked on steel pallets. But just get closer, and you'll feel it. A warmth of energy emanates from them, encapsulated in atoms. Sometimes, instead of ingots, the factory receives aluminum coils. This is already processed aluminum wire, wound into coils 3 or 4 feet in diameter, each weighing about 500 pounds. They shine like snake coils and glisten in the light, as if they just came out of a cybernetic beehive. Separate batches are supplied as aluminum scrap, meaning leftovers from other productions, cuttings, shavings, fragments of frames. They are sorted, cleaned, remelted, because in this future, not a single crumb of metal goes to waste. As soon as aluminum enters the factory gates, it is identified, tested, and marked. In the first stage, technicians inspect the ingots or coils, checking for cracks, corrosion, impurities on the surface. It's like a quick checkup, by eye, by hand, with a scanner. If rust, oxidation spots, or transport damage are noticed, the metal is either sent for remelting or rejected. Next, chemical expertise. A piece of each ingot is taken and checked on a spectrometer. This device shoots the metal with a laser, captures the reflected waves, and shows how much aluminum, iron, silicon, copper, magnesium, and other elements it contains. The goal is to make sure it's the right grade. After passing the tests, the ingots are marked with a batch identification number, alloy grade, date and place of melting, and sometimes a QR code that leads to a full technical passport. It's like a birth certificate that will travel with the metal until the moment it becomes wire and ends up inside a Tesla, Rivian, or Lucid. When the ingots have passed inspection and received their quality mark, they are loaded into giant electric or gas furnaces. The temperature inside, over 1,220 degrees Fahrenheit, is exactly what's needed to turn aluminum into liquid silver. No alchemy. We're talking about molten metal. The damper opens, and massive cranes carefully lower the ingots into the red-hot interior. The metal slowly melts, releasing a gray vapor and a strange smell, a chemical mixture resembling heated foil and ozone. Nearby, operators in heat-resistant suits looking like astronauts carefully monitor the furnace indicators: temperature, impurity level, viscosity. No mistakes are allowed here, as the cable for an electric car must withstand thousands of miles and hundreds of charges. A slag layer appears on the surface of the molten metal: impurities, oxides, residues of alkaline metals. It is removed manually, or by automatic systems to leave only a clean, homogeneous mass. Sometimes, modifiers or alloying elements are added to give the metal the desired properties: more conductivity, strength, flexibility. Molten aluminum is poured into casting molds, usually round blanks 4 to 6 inches in diameter and up to 10 feet long. These are the future rods from which cables will be drawn. The process is called casting billets. Cooling is controlled in stages to avoid cracks. All this is accompanied by hissing steam, the roar of pumps, and a rhythmic thud, the heartbeat of the cable factory. So what is drawing? It's a process where aluminum rods are pulled through a series of increasingly narrow holes. With each pass, the metal becomes thinner, longer, and stronger. Like a piece of dough being rolled out into noodles, only instead of dough, it's hot aluminum, and instead of a rolling pin, hydraulic machines weighing tens of tons. Before drawing, the blank is heated to an optimal temperature, no more than 650 degrees Fahrenheit, so it becomes plastic but doesn't melt. Then it's fed into a drawing machine, where the magical transformation begins. Each pass through the die reduces the wire's diameter by a few percent. It's like passing through increasingly tight doors, forcing the material to stretch. After a dozen such passes, a thick rod half an inch in diameter becomes a slender strand 0.1 inch thick or even less. During drawing, the wire heats up from friction, so it's constantly cooled with water or special lubricants. Without this, it would overheat, lose its shape, or even break. Lubrication also reduces wear on the tools, dies made of carbide or diamond. Some machines can draw wire at speeds over 2,000 feet per minute. It's like someone pulling a spider web from a ball of lightning. Engineers carefully monitor the tension, temperature, shape, and shine of the wire, because even the smallest crack or geometry violation is a future short circuit in a $60,000 car. When the drawing is complete, the cable thread already looks like a shining string for a future electro-magical harp. It's long, thin, conductive, but still stubborn. To be able to wrap around batteries, penetrate narrow body channels, and withstand hundreds of thousands of bends in the motion of an electric car, it needs to be annealed. The wire slowly passes through furnaces without an open flame, or through an induction field that heats it from the inside. The temperature, around 600 degrees Fahrenheit. This is the point where the metal doesn't melt, but changes its character. The atoms, which until now held onto their nodes in a stressed crystal lattice, finally relax. Like soldiers after a battle, like a string that has sounded at its maximum, and finally fallen silent. The metal structure becomes more uniform, the grains larger, and the wire itself flexible, elastic, calm. The surface of the wire after heat treatment is darkish, with scale or signs of oxidation. It is cleaned off with abrasive brushes or in chemical baths. Aluminum must shine, like a star before a rocket launch. The cleaner the surface, the better the insulation will adhere. Next, insulation. An ultra-thin layer of material is applied to the wire, separating it from everything except the current. This can be polyethylene, Teflon, silicone, or enamel, depending on the cable's intended purpose. The material is applied in liquid form, often in heated baths or through nozzles that cover the wire with a uniform flow. The application temperature, over 400 degrees Fahrenheit. As soon as it's applied, it's immediately baked. The insulation doesn't dry, it polymerizes. It's like creating a skin around the nervous system. It must be perfectly even, dense, without microcracks. Otherwise, the wire won't pass the test. Next, the wire passes through detectors that check it for breakdown, coating thickness, and electrical resistance. At least once every 1,000 feet, samples are taken manually and checked under a microscope. Everything is recorded because this wire will later work in high-voltage systems. The finished wire is cooled, lubricated to reduce friction, and then carefully wound onto drums or spools, sometimes up to 5,000 feet long. This is no longer just metal. It's the nerve of an electric car, ready to hit the road. Did you know that each year the world builds structures so massive, skyscrapers scraping the sky, bridges spanning vast canyons, ships larger than city blocks, that they require metal parts shaped with forces equivalent to thousands of tons and precision measured in mere millimeters? This isn't just cutting and welding metal in a workshop. This is bending steel plates thicker than your arm, forging colossal parts under unimaginable pressure, and machining giant structures with surgical accuracy. Get ready to witness the most impressive, largest-scale metal fabrication methods on Earth, uncovering the hidden power and precision that builds our modern world. The sheer scale of metal fabrication hits you right away on the factory floor. We're talking about moving and shaping pieces that weigh tons. One of the most fundamental and visually impressive processes is metal bending. Forget bending a paperclip. Imagine bending steel beams strong enough to support a building, or curving thick metal plates for ships and pressure vessels. Massive machines called press brakes or roll benders use incredible hydraulic force to shape metal. Picture a giant press pushing down with thousands of tons of pressure to put a precise bend in a steel beam, or colossal rollers curving a thick steel plate into a perfect cylinder. These aren't just big tools. They're feats of engineering designed to apply immense force with fine control. On the biggest scale, you see specialized machines like the FKB 3-roll plate bending machine, capable of shaping massive steel plates for tanks, wind turbines, or ship hulls with incredible accuracy. Software like Bentronic controls the rollers with millimeter precision, even on pieces the size of a room. Another impressive example is bending giant steel beams for structures. Machines like the Faction R CMI use powerful hydraulic rolls and guide systems to curve huge I-beams or H-beams into exact shapes needed for complex architecture or bridges. Applying that much force while maintaining the beam's structural integrity is a true industrial art form, making metal flow like clay, but under thousands of tons of pressure. Another mind-blowing method is metal forging. This is using localized compressive forces, often with immense power and heat, to shape metal. Think of a blacksmith, but on a scale where the hammer is a machine delivering thousands of tons of force. In massive forging presses, heated metal billets, solid blocks of steel, are pounded or squeezed into complex shapes. This process changes the metal's grain structure, making the finished part incredibly strong and durable. This is how critical components for aircraft landing gear, engine parts, or even massive artillery barrels are made. At places like the Waterlet Arsenal, you see iconic machines like the rotary forge. This is a different kind of forging, using rotating dies to hammer and shape a heated steel billet into a hollow tube, like a cannon barrel, with incredible speed and precision. These machines have been operating for decades, playing a vital role in producing thousands of heavy-duty barrels for military systems. The sheer force and rhythmic pounding of these colossal machines working on red-hot metal is one of the most dramatic spectacles in metal fabrication, showcasing raw power precisely controlled. Once metal parts are formed by bending or forging, they often need precision finishing. This is where machining comes in, using tools to cut away material and achieve exact dimensions and shapes. On the biggest scale, this involves massive CNC, computer numerical control, machining centers working on parts that weigh many tons. Imagine a machine tool the size of a small house, precisely cutting, drilling, or milling a giant metal casting or forging with micron-level accuracy. Sophisticated software controls these machines, making complex cuts and achieving tolerances required for critical components in aerospace, heavy machinery, or energy production. Precision machining isn't just about size, it's about achieving incredible accuracy on massive objects. Machines use advanced cutting tools made of hardened materials, sometimes cooled with high-pressure coolant, to cut through tough alloys. On critical components like gearbox housings, turbine shafts, or large crane parts, surfaces must be machined to tolerances that ensure perfect fit and smooth operation under immense loads for decades. It's a process where technology allows engineers to sculpt giants with the precision of a jeweler. Beyond these core methods, metal fabrication involves a host of other impressive processes on industrial lines. Cutting is a crucial first step, using powerful lasers, plasma torches, or water jets to slice through thick metal plates with incredible speed and clean edges. Welding is joining metal pieces together, from automated robotic welding arms building vehicle frames or ship sections, to skilled human welders performing critical structural welds that must withstand massive forces. Surface treatment like sandblasting and industrial painting or coating lines protect the metal from corrosion and give it its final look. Throughout all these stages, from the arrival of raw metal plates and beams to the final finished and assembled components, rigorous quality control is paramount. Industrial scanners, ultrasonic testing, X-rays, and precise measurement systems check every weld, every dimension, every material property. Experienced technicians and engineers oversee automated inspection systems and perform manual checks on critical points. A blend of high-tech monitoring and human expertise, ensuring that these massive metal parts meet the highest standards of strength, precision, and safety required to build skyscrapers, planes, and infrastructure. These massive metal fabrication facilities are not just factories. They are cathedrals of engineering power and precision. They process hundreds of thousands of tons of metal each year, shaping it into the backbone of our cities, transportation, and industries. It's a testament to human ingenuity and technological advancement, taking raw materials and applying immense force and incredible accuracy to build the physical world around us. It's a hidden, necessary industry that few people ever see. So, the next time you look up at a skyscraper, cross a bridge, or see a large machine at work, remember the mind-blowing industrial process that created its metal bones. The bending of giant beams, the forging of colossal parts, the precision machining of massive structures. It's all part of the amazing world of metal fabrication. It's a fascinating look into the power and precision that builds our modern world. What part of these impressive metalworking methods surprised you the most? Let us know in the comments. Now, can you just picture this? Every single day on this planet, folks burn through over 9,900,000 barrels of oil. That's like what? 1 billion liters. Pretty wild to think about, right? But what is oil, really? How does this thick black goo actually get turned into the energy that powers our entire world? Today, we're gonna dive deep into the seriously fascinating world of oil production. We'll start with how it even forms over millions of years, then check out the incredible tech in modern wells that punch down tens of thousands of feet into the earth. We'll cover everything from those giant platforms way out in the middle of the ocean to the complex refining steps that take that raw material and turn it into clean fuel. Ready to find out the real story behind that black gold? Let's just jump in and see how natural gas really works. Folks are projecting that average oil production in the United States next year is going to hit right around 9,900,000 barrels per day. But honestly, do you even know what oil is or where it even came from in the first place? I mean, everybody talks about oil this, oil that, oil spills, oil production. But nobody ever really tells you what it actually is. Well, stick with us and we'll just break it down for you. The way oil forms is a seriously long-term project, taking millions of years. It kicks off with a bunch of organic stuff, like the leftovers from ancient plants and little critters, piling up on the bottom of old seas and lakes. Over time, these plant and animal remains get buried under layers of sedimentary rocks, things like clay and sand. Then, under a ton of pressure and heat, which gets way more intense the deeper you go, that organic material starts transforming into something called kerogen. It's kind of a solid, waxy material. If the temperature keeps cranking up, hitting somewhere between 140 and 302 degrees Fahrenheit, that kerogen breaks down using heat. And bam! You end up with liquid hydrocarbons. So, yeah, that's us your oil. If you didn't find that interesting, seriously, let us know what you think is cool. Just write it down. Okay, so the oil that formed just like we explained, it actually travels through porous rock until it runs into something called a trap. Think of that as a geological structure that just stops it from moving any further. It starts building up there, and bingo, you've got yourself an oil field. It's kind of fascinating that scientists are still having debates about the exact details of this whole process, and whether oil might form in other ways too, not just from ancient organic bits. People started pulling oil out of the ground way back in ancient times. But the real deal oil boom didn't kick off until the 19th century. That's when the kerosene lamp came along. To actually get your hands on the oil, the absolute first step is figuring out precisely where it's hiding. This phase, geological exploration, is easily one of the toughest and most expensive parts of the entire oil extraction game. Scientists aren't just walking around with shovels, you know? They're using satellite images, magnetometers, seismic waves, and other super high-tech methods. Seismic surveying is actually pretty spectacular to witness. They set off controlled underground explosions in a specific area, or use special vibrating platforms to create waves that travel down through the rock layers. These waves bounce off different layers in the ground and come back up, and sensors pick them up. It's like building a three-dimensional picture of what's underground, essentially letting them see beneath the surface. Once the geologists pinpoint a promising spot, the actual drilling kicks off. A rig, whether it's sitting on land or floating out in the ocean, turns into this giant humming machine that runs non-stop 24/7. The drill string, those are steel pipes with a cutting bit on the end, bores into the earth, spinning at up to 200 rotations per minute. To keep the drill bit cool, carry rock pieces out, and stop the hole from collapsing, they pump in drilling mud. That's a thick mixture, usually water or oil-based. Modern wells can go seriously deep, ranging from 10,000 feet down to 16,000 feet. And sometimes, way deeper, up to 35,000 or even 40,000 feet. For instance, over in places like Texas or Saudi Arabia, they're drilling wells that stretch over 26,000 feet long. And often, a big section of the well goes sideways, horizontally. This lets them tap into a much bigger chunk of the oil reservoir without having to drill a bunch more vertical wells. One of these operations can cost you anywhere from a few $1,000,000 to easily tens of millions of dollars. And honestly, it doesn't always work out successfully. But if the well does turn out to be a producer, oil starts making its way to the surface, either pushed by its own natural pressure or pulled up with pumps. And that's when the next big stage begins, actually getting the oil out, processing it, and shipping it off. Speaking of major producers, Saudi Arabia is right up there as one of the biggest oil producers globally. Just back in February, Saudi Arabia was pumping out nearly 9 million barrels of oil every single day. This country actually has a solid chance to boost its standing in the energy market even further, especially since Saudi Aramco recently announced they found 14 brand new oil and gas fields right there in the country. So, once all the exploration and well drilling is completely finished, the absolutely crucial stage begins, actually pulling that oil out of the ground. If the field is really rich, the oil itself might just start pushing its way up to the surface simply from its own pressure. That's what's traditionally called a gusher. And while it might look pretty dramatic, with those big streams of black liquid shooting up into the air, these days, that method is seen as pretty old school and kind of dangerous. Modern wells are outfitted with sophisticated systems of valves and regulators that allow them to precisely control the pressure and the volume of oil that's flowing out. The oil gets to the surface through a network of pipes, and then it heads over to what's known as a processing facility. That's where they separate it from other stuff that came up with it, like associated gas, water, sand, and whatever else is mixed in. This step often happens right there at the extraction site, either on those big platforms out in the ocean or at bases on land. Separating all those impurities is a pretty cool process to watch. The oil mixed with all the extra stuff goes into this large, sealed tank, and gravity gets to work inside. Gas is light, so it floats up to the top. They collect it through an upper outlet. Water is heavy, so it settles down to the bottom. They drain it off through a lower valve. Oil is in the middle in terms of density, so it hangs out between those two layers. Now, if tiny droplets of water get kind of stuck in the oil, it's not quite as simple to separate them out. That's when they might add something called demulsifiers. These are chemicals that break up that mixture. Or they might heat the oil up a bit, which also helps those different layers split apart. But hey, let's get back to the extraction itself. Sometimes, to increase the pressure down in the rock formation, they use what are called secondary recovery methods. For instance, they might pump water, gas, or even steam into other wells. This helps to kind of push the oil towards the well they're actually producing from. Technologies like this can help them pull out up to 60% of the oil reserves from a field, whereas without them, that number could be cut in half. The average amount of oil a modern well in the United States produces is anywhere from 500 to 1,500 barrels per day. Just think about that for a second. 1 barrel is 42 gallons. Now multiply that by the thousands of wells operating all over the planet, and that really gives you a sense of the true scale of oil extraction. Oil by itself is actually a really complex blend of hundreds of different hydrocarbons, ranging from those lighter gases all the way up to heavy fuel oils. To get gasoline out of it, that's that light, easily ignitable part that internal combustion engines can use effectively. The raw material goes through several technically tricky stages at an oil refinery. It all kicks off with something called fractional distillation. Crude oil is first heated up to temperatures between 660 and 750 degrees Fahrenheit and then fed into a distillation column. This is a tall tower where the temperature gets cooler as you go up. Different components of the oil vaporize and rise to different heights, where they cool down, turn back into liquid, and are collected at various points. The gasoline part, it's one of the lighter ones, is typically collected at levels corresponding to temperatures between 104 and 392 degrees Fahrenheit. But simply distilling the crude oil isn't quite enough to get high-quality gasoline. You only get about 15 or 20% of the gasoline fraction this way, and most of what comes out still has stuff you don't want in it, and an octane number that's just too low. To boost the total amount of gasoline they get, they use a process called cracking. This is basically all about breaking down those long hydrocarbon molecules into shorter ones. The most common way is catalytic cracking, where heavier parts are heated up to almost 1,000 degrees Fahrenheit in the presence of catalysts. This lets them get extra gasoline from those heavier leftovers. Sometimes they also use hydrocracking, which involves hydrogen under high pressure. When it's all said and done, the percentage of gasoline you can get from just 1 ton of oil can reach 40 or 50%. That depends, of course, on the type of oil and how sophisticated the refinery is. The gasoline they get from these cracking steps usually has a low octane number, meaning it would cause knocking or detonate too early in an engine. To fix this, they put it through a process called reforming. This means rearranging the structure of the molecules at high temperatures, usually with platinum catalysts present. This really boosts the octane number, potentially all the way up to 98, making the fuel perfectly suitable for today's cars. In the very last step, they mix additives into the gasoline to improve how it works. This includes things for anti-corrosion, preventing engine knocking, cleaning the engine, and reducing environmental impact. This helps keep the engine healthy, cuts down on harmful stuff coming out of the tailpipe, and makes the fuel more efficient overall. Just one modern oil refinery can process up to 400,000 barrels of oil every single day. That's pretty impressive, especially when you stop and think that daily gasoline consumption in the United States is roughly 370 million gallons. Besides going to our homes, natural gas also gets sent to power plants, factories, and chemical facilities. For big industrial users, they need way higher pressure and volume. They're using pipes with diameters up to 48 inches and pressures up to 1,500 psi. Gas can even be turned into a liquid. They cool it way down and ship it in massive tankers across the oceans. Imagine this: red-hot metal, up to 33 feet long, being pushed with a dull roar into a massive rolling mill. No seams, no joints. Just a perfectly smooth steel pipe appearing literally out of nowhere. These aren't scenes from a science fiction movie, but the daily work at one of the most unique factories in the world. How is it possible to create a pipe without a single seam? One that withstands pressure of hundreds of atmospheres and operates where other materials simply melt. Ready to walk through the scorching workshop and find out how true engineering perfection is born? Then let's embark on a journey to an amazing steel pipe factory. It all starts with cylindrical billets. Each one weighs 1 ton. That's like 3 smart cars in a metallic body. They are transported by rail or truck because other transports simply can't handle such a load. Each billet is secured on special pallets or in retaining clamps so it doesn't shift during movement. Upon arrival at the factory grounds, unloading is automated using cranes, manipulators, or hydraulic carts. The billets immediately go to the receiving area, where they are checked for compliance with technical specifications, chemical composition, shape, integrity. Before the hot steel becomes a pipe, it undergoes a truly dramatic inspection. Defects shall not pass. First, the billets get an X-ray. Well, not exactly X-ray, but something similar for metal. Ultrasonic testing. You heard that right. The billet is coated with a conductive gel, like for a human ultrasound, and a transducer is moved across it. Special transducer ears shoot sound waves at a frequency of 5 MHz. That's 100 times higher than submarine sonar. This is how they search for cracks and inclusions of foreign materials within the billets. The system builds a 3D map of defects with an accuracy of 1/100th of an inch. If it finds a saboteur, the billet is marked with red paint and sent to metal hell for remelting. Next comes the chemical analysis. For this, 5 or 10 metal samples are taken from each batch and sent to the factory laboratory. There, they use special spectrometers, devices that read the metal's composition using light emissions. The spectrometer determines over 12 elements in the composition in seconds. During the analysis, the sample is treated with an electric spark or a laser. This excites the atoms on the metal surface, causing them to emit light of different wavelengths. Each chemical element glows uniquely, so the device recognizes exactly which elements are present in the steel and in what quantities. How much carbon, manganese, chromium, nickel, or phosphorus. This analysis takes only a few minutes, but provides a complete picture of how well the billet meets technical requirements. If the composition isn't perfect, the batch might be rejected or redirected to other production lines. From 1 to 3% of billets are sent for remelting. Defective billets are sent to an electric furnace with a temperature of 2,900 degrees Fahrenheit, where the steel becomes liquid again. All the post-melting slag is used for road construction. 90% of defects are detected during the ultrasonic diagnostic stage. It's like finding a needle in a haystack in 10 seconds. The chemical analysis takes 17 seconds, faster than you order coffee at Starbucks. Quality control costs range from $50 to $100 per ton of steel, but it's better to overpay than to later have a well blowout due to low quality material. Quality control is the Karen's filter for steel. Only 97 to 99% of billets become pipes. The rest are sent for reincarnation. So, when you hold coffee in a steel thermos, know this: its ancestors went through real metal special forces training. After checking the chemical composition, the cylindrical steel billets are delivered to the heating section, the place where a giant furnace stands. These furnaces are true giants, capable of holding over 1,000 billets simultaneously. To load the billets inside, massive automated cranes or special manipulators with heat shields are used. The billet is picked up using gripping mechanisms, large metal fingers or tongs that securely hold the heavy part. The crane carefully moves the billet to the open loading door of the furnace. At this time, the temperature inside can exceed 2,400 degrees Fahrenheit, so the entire process is maximally mechanized. People operate the machinery remotely from a safe cabin or control panel. The furnace has special guides or pushers that help place the billets carefully inside, so that heat distributes evenly. After loading, the furnace doors are hermetically sealed, and gradual heating to the working temperature begins. In 2 hours, the steel transforms into a plastic mass. The billet becomes ready for forming, like melted chocolate. Next, the monster drill comes into play. It weighs 12 tons. That's like 2 elephants. The red-hot steel billets, massive cylinders, are removed from the furnace and delivered to a special rolling machine, where one of the most crucial stages of seamless pipe production begins, creating the hole inside. The piercing process looks impressive, The red-hot billet is placed on a special support ring in front of the piercing mill, where a thick, cone-shaped rod awaits it, the so-called piercer point or piercing mandrel. At this moment, immense force is at work. The billet is rotated between two conical rolls, spinning in opposite directions. The rolls don't just squeeze the billet, they create strong rotational and axial pressure, causing the billet to stretch along its axis, flowing around the piercer point. To avoid cracks or ruptures, the pressure and temperature during piercing are controlled very carefully. If the billet cools too quickly, or the pressure is distributed unevenly, it can break or lose the required shape. Therefore, the process runs without interruption, and with strict adherence to all parameters. This process is called the Mannesmann method, named after the German engineers who invented it in 1885. After the initial piercing, the resulting rough pipe is called a hollow shell or bloom. The wool thickness of the shell is approximately 2 inches. It still has uneven walls and may contain small defects, so the next stage is rolling and calibration, where the pipe is stretched, straightened, and brought to the required dimensions and wall thickness. The red-hot steel billet enters under giant rolls 5 feet in diameter. Under tremendous pressure, it's drawn out into a slender pipe up to 40 feet long, faster than you can blink. This is where the major league of precision reigns. Wall thickness is reduced from 0.8 inches to 1.2 inches, with a deviation of less than 4/1000ths of an inch. That's thinner than a human hair. And all this happens at staggering speeds of 16 to 49 feet per second. Faster than Usain Bolt on his best day. It's like rolling out the thinnest pizza dough. Only instead of dough, it's a red-hot steel core. And instead of a kitchen board, there's a shower of sparks and the roar of the rolls. Next, fire gives way to ice. Well, not ice, but cooling. The workshop heat is 122 degrees Fahrenheit, so workers wear special suits as if preparing to conquer Mars. Meanwhile, the pipes gradually cool in the open air. Their temperature slowly drops to 570 degrees Fahrenheit to avoid deformation and cracking. When the pipe emerges from the fiery dance of rolling, it resembles an enraged dragon, powerful, but bent into wild spirals. That's when the 8-roll giant enters the scene, a mechanical Hephaestus that will forge perfect forms. Its rolls, stronger than the rocks of Olympus, bend the steel with a force of 500 tons. That's like putting 250 Land Rovers on the pipe. But this force isn't a destroyer, but a surgeon. It corrects curvatures smaller than the thickness of a hair. And then comes the time for lasers. They scan every millimeter, finding the smallest defects, invisible cracks, minor unevenness. And when they find something, plasma scalpels enter the game. 10 times hotter than lava, they cut the metal like cosmic lightning bolts. All that remains of the defects is smoke and legend. If the Colossus of Rhodes were made of such pipes, it would still be standing today. Imagine taking the air you are breathing right now and turning it into a substance that can freeze ice cream in 3 seconds and make a banana tough enough to hammer nails. This is not magic. It is liquid nitrogen. Every second, it is used in medicine, science, the food industry, and in some top-secret experiments. Temperature, minus 321 degrees Fahrenheit. 1 sip, and you lose part of your stomach. 1 breath, and you unlock tomorrow's technology. How does the coldest substance on Earth get made from regular air? How is it transported, stored, and used? And why can it save or destroy? Watch closely and prepare to be amazed. It all begins with air. Yes, the very same atmospheric air that surrounds us. This happens inside industrial air separation units. These systems come in all sizes, from massive factory installations to mobile units for medical use. Air is sucked in using compressors. Then it passes through filters. First, coarse filters that remove dust, insects, and pollen. Next, fine filters get rid of moisture, carbon dioxide, and other impurities. Once cleaned, the air is compressed using powerful machines, increasing both pressure and temperature. Then, it is gradually cooled in heat exchangers. When the high-pressure cooled air moves through a narrow nozzle into a low-pressure chamber, it expands rapidly. That sudden expansion causes a major drop in temperature. This is the key moment. The gas becomes cold enough to start condensing into a liquid. This process repeats several times. Each cycle drops the temperature further. Eventually, nitrogen reaches its liquefaction point. This technique does not work with every gas, but it is perfect for nitrogen. Thanks to this, we can create liquid nitrogen from ordinary air. Once the air is chilled and liquefied, it goes through fractional distillation. This process separates the liquid mixture into components based on their boiling points. Inside a special distillation column, the liquid air is gently reheated. Nitrogen has the lowest boiling point, around -320 degrees, so it evaporates first and rises to the top. Oxygen boils at -297 degrees, so it evaporates later and does not climb as high. Argon, with a boiling point around -302, settles somewhere in between. The column forms a thermal gradient, colder at the top, warmer at the bottom. The gases evaporate and condense over and over, becoming purer with each cycle. It all works without additives, automatically, and with minimal losses, thanks to precisely managed pressure and temperature. Since nitrogen makes up roughly 78% of air, extracting it takes powerful equipment, a complex network of pipelines, and exact temperature control. Once separated, liquid nitrogen is stored in special vessels, cryostats, or Dewar flasks, which look like futuristic thermoses. These vessels keep temperatures low and prevent evaporation. They are not just metal barrels. They have double walls with a vacuum in between to block heat. Some also include reflective coatings to minimize radiant heat loss. These containers can preserve liquid nitrogen for several days to several weeks, depending on volume, insulation, and how often they are opened. Often, nitrogen is used right on site. For example, medical facilities use liquid nitrogen for cryopreservation of cells, embryos, vaccines, and tissues. In the food industry, it is used for flash freezing. Contact with liquid nitrogen instantly freezes food, locking in texture, taste, and shape. But when it needs to be transported, preventing evaporation is critical. That is because nitrogen quickly turns back into a gas. Portable dewars, cryotanks, and cryotank trucks are used. Small dewars are handy for labs and clinics. Cryotanks are massive, like giant gas tankers, and are hauled by trucks with special mountings and ventilation. Cryotank trucks are purpose-built vehicles with insulation and pressure regulation to avoid explosions from expanding gas. Sometimes, liquid nitrogen is produced directly on site, at large research centers or hospitals, to avoid reliance on deliveries. How did humanity tame one of the coldest, most inert substances on Earth? It all began with nitrogen. Discovered in the year 1772 by Scottish chemist Daniel Rutherford, who was studying air and found a gas that could not sustain fire or life. That was nitrogen, colorless, odorless, inert. But liquefying it required cold and pressure, and humanity needed more than 100 years to figure that out. The first liquid nitrogen was produced in 1883 by Polish scientists Zygmunt Wroblewski and Karol Olszewski. They built a system that cooled air so much that nitrogen, its main component, turned into a liquid. That was a breakthrough. In the 20th century, cooling tech advanced fast. Scientists improved gas liquefaction methods and eventually developed the Joule-Thomson cycle, which relies on pressure drops to efficiently liquefy gases. In the 1930s and 50s, liquid nitrogen made its way into industry and medicine, starting in labs, then into surgeries, biobanking, and physics experiments needing ultra-low temperatures. Today, liquid nitrogen production is a global-scale operation. It is made in massive air separation plants around the world. What was once just background gas, making up almost 80% of air, has become a superstar of industrial science. Some chefs even make ice cream live, pouring cream into a bowl, adding liquid nitrogen, mixing, and voila, instant dessert. The cold is so intense, it freezes the treat in seconds. Dip a banana in liquid nitrogen for a few seconds, and you can hammer nails with it. Seriously. Want to try? Inhaling cold nitrogen vapor can temporarily change your voice, like helium, but deeper. But do not try this. It is dangerous without protection and special equipment. Some people have dipped old socks into dewars of liquid nitrogen. Result? The fabric becomes brittle like glass and crumbles in your hands. A perfect way to destroy evidence. If you are a sock. Pour liquid nitrogen on a warm floor, and it turns into a dramatic cloud. It vaporizes instantly, making you feel like you are stepping through a Hollywood portal. What should you never do with liquid nitrogen? Even if it looks cool, never stick your hand into it. Online videos show people dipping fingers and pulling them out unharmed. That is the Leidenfrost effect. A brief protective vapor layer forms around the skin, but if you hesitate for a second too long, hello frostbite, do not try it. Seriously. Never drink it. Yes, that happened too. In several restaurants, smoky desserts were served with a drop of liquid nitrogen. One careless guest sipped before it had fully evaporated and lost part of their stomach, literally. Afterward, several countries banned such stunts. Do not pour it on your bathroom floor. The vapor looks cool, sure, but tiles can crack from thermal shock. Plus, the risk of suffocation in a small space is real. Nitrogen displaces oxygen. Do not pour it in the toilet. Not because it will definitely break, but it might. And because pipes can burst. Some TikTokers have proudly frozen their plumbing. Utility crews must love them. If you are not an engineer or a molecular gastronomy chef, do not try freezing food or fruit from the inside. Liquid nitrogen can rupture the skin and explode in your hands, especially with high moisture items. So yes, liquid nitrogen is amazing, but it is also incredibly dangerous. Respect the frost.